Okay, so we're going to get started. The topic for today is dynamic resting state connectivity. I think a couple of lectures ago, Katie Chan introduced the concept of resting state connectivity, and today we're going to get into a little bit more detail about it. What I have prepared for the talk is basically distributed in three main blocks. First is, it's kind of for those of you who are not familiar with what this concept of functional connectivity dynamics is, kind of a definition, pseudo-formal, and then go through some of the original observations that once that this phenomenon was observed, they went into the basic characterization. From there, we'll move into trying to understand or better understand whether this is something that we should be spending our time on or not, meaning is there a relationship between these connectivity dynamics that we observe and something like cognition or disease, which are the final goals of why most of us do fMRI. And then at the end, if I have time, I'll go through some comments on methodology. There's been a couple of main ways of doing this, and recently there's been a lot of attention about whether those are the best ways to do it or not. And I'll have a couple of comments on that, and then we'll go into conclusions. And please, at any moment, feel free to stop me. If you have a question, please go and stand up and talk to the microphone so it can be properly recorded. Okay, so what is functional connectivity dynamics? So here we have a brain. And here we have the time series for a seed ROI within the posterior cingulate cortex. And the common practice in resting state fMRI until recently was that we would take our whole time series and compute our maps of connectivity or do our ICA or whatever that we're willing to do under the assumption that it was better to use the whole duration of the time series because what we were looking at was a stationary process, and therefore the more data points that we input, the better to get a clear and less noisy picture. That being said, which might be correct potentially, the truth is that if we compute, so on the top, we have the map of connectivity that will come if we were to use the whole time series here. Here it's an hour, but it could be your normal 6 minutes, 10 minutes of rest data. And we get our default mode network and a couple of other areas. But if we were to do the same thing and only do it on the first 5 minutes, or the last 5 minutes, or this intermediate 5 minutes, what we would see is that the maps that we get, although consistent to a given extent, they show a lot of variability. And this whole field of resting state connectivity dynamics is understanding whether this is a characteristic of the brain or simply a result of the noise in the data. And if it is the first one, which to a given extent it is, then what are the best ways to looking at it and make some sense and potentially even use measures of this variability as biomarkers. So let's go through some of the original studies that capture this phenomenon of resting state connectivity. One of the first one is the one by Katie Chan back in 2009. Here we have the time series for two different ROIs. One is the PCC and another one is some ROI somewhere else in the brain. And just by looking at them, we can see that there are periods of time where they seem to be going together quite well, basically maybe around here. But then there's other periods of time where very clearly, the signals don't go together anymore. And that's what we're talking about. One way of putting a number or better way of looking at this that's simply looking at the time series to compute this sliding window time series of correlation. You just capture a subset of the signal, maybe from 0 to 100, compute a correlation value, you move one step, from 1 to 101, compute a correlation, and then you get these traces of how the connectivity evolves across time. If we were to do this, and of course here we start getting into some of the methodological considerations, what is this optimal window, what is the step between windows, it's actually this the best way to do this, or just by doing this sliding window, we should expect that we're going to see some non-constant behavior in the correlation. But we will talk more about that later. But just for now, here what we can see is that definitely the correlation when we look at this level is not a constant value. There is a lot of variability. And it seems that, for example, what I was saying here, this period here where the signal seems to go anti-correlated, translates when we do this type of analysis into the correlation going down below 0. So that's one of the first observations. What they also saw on this paper is that variability that I just described, it's not the same all over the brain. If we were to do that type of analysis from the PCC to every other single location, and then potentially look at the strength of that variability, maybe the standard deviation of those, time series of correlation, not the original time series, we would see that different regions in the brain have different levels of variability. Again, something interesting and potentially worth looking at. Maybe a difference in variability is something good, or maybe we can find that across normals and patients that variability disappears. Those are the type of things that people think about when looking at this data. What they said on this original paper, and I think it's very important, it's unclear whether the observed coherent or phase variability or correlation variability can be attributed to residual noise, or it's truly the result of modulation of cognitive states or mental processing. So that's something important to keep in mind. We have to dig deeper. Just because we observe this doesn't mean this is telling us something about the brain. And they also illustrate in the positive way that resting state functional connectivity maybe is not static and maybe valuable to consider those measures of variability. So they really hint at everything that the field is these days. So let's look at this in another way. Another way of showing how much this variability is not only there, but it's quite strong, is you can think of doing this. You get a brain, you define your ROIs, you strike your time series for each of the ROIs, and then you compute for it, let's say, every minute, the correlation of everything to everything. You get your matrix of correlation. Those are symmetric. You can get the top of that matrix and plot it as a vector, and then basically you can get one of those plots in which this matrix is no longer ROI to ROI, but basically this is time in terms of window number, and its column here is that a snapshot of the connectivity of the whole brain to each other for that window. And you can see that this is not flat across the horizontal direction, but actually you can see that there are periods here where there is a strong connectivity in these connections, then this appears, then it comes back. If we were to take one of these columns and put it back into the connectivity matrices that we're used to see, what we see is that these matrices are quite different across time. So we have variability, and we have variability that is quite big sometimes, and that it actually differs quite a bit from the pattern of connectivity that we would have calculated should we have used the whole time series as a single unit to analyze. Not only that, people decide to look at this dynamic behavior in awake humans, in anesthetized monkeys, and it seems that this variability is always present. That is something to consider when we want to interpret it. Here in our lab, one of the first things that we decided to do is to go a little bit deeper into trying to understand whether the variability has some spatial structure and whether that structure tells us something about the brain or agrees with what we know already. And we decided to look at the variability across these 1 hour scans that I showed you before and try to look for which were the most stable connections and the most variable connections, and that those most stable and most variable, we only talk about them if that was a finding that was consistent across all the subjects that entered this study. And what we saw here, so here you have a matrix in which the color here indicates the stability, and what you can see here is that for the most stable connections, a lot of them are connections that are within the networks, which makes sense. I mean, if a network is to appear as a cohesive set of regions, when you consider the whole time series, it has to be that even at certain periods, to a given extent, they have to be cohesive. If they're not at no point, then they wouldn't appear. But that being said, we can also see that there are some other that are connections across network that seems to be among the most stable. And we can also see that not every single connection that is part of a network made it to this subset of the really, really very stable connections. In terms of the spatial profile, what we found is that mostly symmetric interhemisphere connections between homologous left and right regions seem to be those that are most stable. And that these most stable, as I just said, only account for a small percentage of its intra-network connections, which means that these networks are flexible over time. And it seems that unimodal sensorimotor network seems to be the ones that contain most of those very stable connections. For the least stable connections, the picture is completely different, and the common finding across all subjects was that most variable connection corresponds primarily to internetwork, interhemispheric connections involving frontoparietal networks and occipital regions, and also some of the DMM. With a completely different approach about how you compute that variability, there's been other studies that have also found that this kind of frontoparietal region seems to be the ones whose connections are among the most variables in these short temporal scales of within a run. And it's interesting that that agrees with some other studies that have looked to variability across subjects. This is no longer dynamics, but what are the regions whose connection is the most variable across subjects? And you tend to always see in these frontal and parietal regions. And in this particular study, which I do recommend to read, they found that those are actually the regions that they had the latest development, evolutionary speaking. So we start to see that variability that we see, it seems to have some structure. This is not enough to claim that this is something we should spend in our time on, but we're gonna go step by step towards hopefully finding that variability at the scale of what's within a run might be something that is worth looking at and has information about the brain. In a completely different study, they also decided to look at this concept of dividing connections in 3 different types. They talk about interhemispheric connections between homologous ROIs, and those are these guys in red, similar to the ones that I just showed you in our study that were the most stable. They also look at interhemispheric connections between non-homologous ROIs, and they also look at intrahemispheric connections, okay? And when they do that, and they did in 2 different data sets, one in human data and one on macaque, they found that in all instances, it seems to be these across hemisphere homologous connections that are the most stable. Here, the higher the number, the higher the stability, okay? And that was consistent across resting scans, and I believe this was one task-based scan, and also between the human and macaque data. But they went one step further, and they actually had some information about how anatomical metrics of axon density, percent myelination, and axon diameter vary across the corpus callosum going on an anterior-posterior direction, and they were able to find some correlation between those structural metrics and the pattern of stability, again, as you move from the posterior to the anterior part of the corpus callosum, coming to the conclusion that it seems that to a given extent, what we see, it's somehow related, or at least agrees partially with what we know anatomically. Again, one step forward. But when you all do all those things, and I hope this is one take-home message if you decide to explore connectivity dynamics, it's very important that you think about all potential other reasons that might have affected the results. Call it artifacts, or in this case, they decided to look whether distance, that the length of those connections was a factor. And they found that even though you can see a slight correlation here, the truth is that those very stable connections are distributed across all potential distance. So that's one good extra point to see that at least this was not a potential confound on the data. So, okay, so we have that there is variability, that this variability is strong, that this variability we can find it in anesthetized animals, in awake humans. It also seems that there are some correlates with anatomy. The final observation that I think is the one that has captured the attention of most people is this idea that if you were to look at the connectivity of the whole brain, and look at the dynamic behavior as a scan progresses, you would find this thing called functional connectivity states, which is a series of recurrent short-term whole brain connectivity patterns that are not only present in each of the subjects, but that it can be to some extent reproduced across subjects. So the whole idea is that here you have your time series, here you have a given parcellation of the brain, and either doing this type of a sliding window analysis or some other analysis for subsets of your run, you come with these overall patterns of connectivity. And then if you were to look at them and attempt some sort of clustering, what you would find is that there are a subset of kind of representative whole brain connectivity patterns that seems to occur for short periods of time, then reoccur later, and that actually those patterns, to a given extent, you can find them to be reproducible across subjects. In the original study that talked about this, they particularly found 7 of those functional connectivity states. Please don't get hung up with that number. It may be 7, it may be more, it may be that varies by subject, but they found these 7. And initially, one thing that they found that seems very interesting was that this was this particular state whose spatial pattern of connectivity agrees with what we know, of what happened when people get more drowsy. And they found that that particular stage seemed to be occurring more and more as you look at later points within the scan. So again, you find something that it's hard to interpret, especially when you're looking in rest data, because it could be anything. It could be driven by the noise. It's really a good idea not just to stop there, but try to interpret it within something else for which you have information and that you can then ensure it's just not simply an artifact or the result of taking a lot of data, running through a block pipeline of analysis and some pretty pictures coming out. Okay, so at this point, I hope we have some intermediate conclusions. First of all, functional connectivity exhibit a rich dynamic behavior at the scale of minutes to seconds, so within a run. It's present both in awake humans as well as anesthetized macaques. These observed short-term patterns of functional connectivity can deviate significantly from average stationary functional connectivity patterns. These functionally connectivity dynamics have they have non-random spatial patterns such that we can find that interhemispheric homotopic connections are among the most stable and heterotopic connections about the most variable. And then, people have found those correlates with either measures of variability across subjects or even evolutionary cortical expansion. And then there is this concept of functional connectivity states in which I'm going to go a little bit deeper. So any questions so far? Okay, so I'll continue. Okay, so the second part of the talk was this idea of, okay, so they're there, they seem to make sense. So what has people done in terms of trying to map them towards something either behavioral or clinical? And before we do that, and I'm trying to make this point many times, it's good to be aware that just seeing this dynamic behavior, which is very appealing, doesn't mean it's real. So here we have two time series. This is data provided by Dan Haberker, and we have two time series, we have their spectrum, and if we were to do this sliding correlation, we have this wonderful trace in which we seem to see that there are periods in which connectivity goes up, others in which come down, and it's kind of smooth, so we might want to make something out of it. If we were to convert these two time series into their frequency, take the magnitude and keep it the same, but randomize the phase and go back in time, which basically destroys any temporal information, we'll get a different trace. But if I only were to give you the blue one, initially you might try to make sense of it as much as you would have tried to make sense of the blue. I do it again, and a completely different one. So regardless of whether or not these things are due to neuronal interaction, just be aware that two random time series can show what seems to be appealing sliding window correlation dynamics, okay? That being said, that doesn't mean that when you see them every time they run, and if you can match them to behavior, to other things, then they might be meaningful. But it's good to think that maybe we always have to control for a lot of things on fMRI. I would say here, just give it an extra thought. So on the positive end, so people have found relationships between functional connectivity states or dynamics and a lot of things. So this is a very nice study in which what they try to do is to try to stage sleeping stages based on fMRI and based on this concept of functional connectivity states. So the first thing in this experiment that we need to be aware is that they did concurrent Ball fMRI and EEG. With the EEG, there is standards about how to stage the different levels of sleep, and that's what they did first. So they have this information as the scan progresses in which of the different sleep stages they think their subjects are, taking out from the EEG part of the data. Then they went into the fMRI part of the data, and they first selected a series of ROIs based on the literature that they know are the type of ROIs that you would be interested in if you were to study sleep or changes in drowsiness. So what I mean by this is that this study, we're not looking at the whole brain like they did on the original study that defined functional connectivity state, but they're restricting it to a subset of ROIs. And there's nothing wrong with that, but it's a limited picture from that point of view. And what they do is for those 22 ROIs, using a sliding window correlation, they compute the connectivity matrix. And then they use a classifier that they train it with a subset of the data, the labels of which of the sleep stages comes from the EEG recordings, the fMRI data comes from this kind of restricted connectivity analysis, and then they try to test on the remaining of the data. And what they found is here you have the actual stagings for based on the EEG, and here you have the outcome of the classifier, and it seems to agree quite well. And they found that actually for a window length of approximately 2 minutes, they were able to find accuracy of around 80%. So it seems some information is there. We decided to do our own take on trying to explore the validity or the meaningfulness of this concept of functional connectivity states. In our case, we decided to scan subjects continuously for 25 minutes, and we asked subjects to do 4 different things for blocks of 3 minutes. The idea here was that if we were to do rest continuously, it's really hard to know what's the ongoing cognition. I can pass a questionnaire at the end, I might get some information of what they were doing on average, but to have a clear picture of from minute 1 to minute 5, you were thinking about your past. From minute 5 to minute 7, you decide to count backward. It's hard. So we decided to impose these cognitive states by means of tasks, which really bring us completely outside of rest, but it's a good well-controlled environment to test this idea whether whole brain connectivity patterns at really short scales actually reflect ongoing cognition. So we decided to impose 4 mental states, one of them very unconstrained rest. Another one was a memory task. Another was a visual attention task in which they see a video of a fish tank, and from time to time there would be a crosshair and they have to press a button depending on the type of fish. And then another one, it's a math task. So we do this continuously for 25 minutes. For each of the moments in which subjects are meant to be in a given mental state, we have 2 occurrences at different points within the scan, and these occurrences are not always preceded by the same task. So as you can see here, the video here is preceded by the math, but here the video was preceded by the memory, and so on. And then we can take this data, in this particular example, subdivide it in maybe, 45-second windows. So we get 4 of them within each block of 3 minutes. We get the connectivity matrices for each of those windows. We take the top triangle of this matrix, put it as a vector, and think of those vectors and those snapshots of connectivities for each of these windows. In this case, it's not really a sliding window because those are not overlapping windows. It's just we took all the data, we divided it in chunks, in non-overlapping chunks of 45 minutes, and for each of those, we have a vector that represents how the whole brain is interconnected within those 45 minutes. We can take those, put it all together with no information about what the subjects were doing, give it to a clustering algorithm, and the idea was that if I give all these, I will have to do the math, but whatever, 60 vectors, assuming I have 60 windows, and I give it to an algorithm and say group it in groups of, group it in 4 groups, with no information about when in time those things are coming or what was the task that was being done. If the groups happen to be in such a way that all the vector that corresponds at the moments in time when the subject were resting end up in the same group, all the vectors corresponding to the moments where the subjects were doing the visual attention task end up in the same group, and so on, that means that there is information there about the cognitive state. If when I do this, things end up all over the place, then it's hard to argue that that information is being reflected in the functional connectivity states. That being said, because here there is no training, it's just simply clustering, what I end up is with 4 groups. Just by doing this, there is no way that I know that what I call here functional connectivity state 4 actually refers to rest, okay? That's a drawback of this approach in which this is not really, a classifier, but just simply clustering of things. So what we did later is basically we did this analysis and then we computed some metric that allowed me to compare how well this type of grouping agrees with the type of grouping that me as the experimenter would have done, knowing each of the windows to which of the task corresponds, taking into account potential agreements just simply due to chance. And when you do that, and we did this for several window lengths, which end up with several amount of vectors that you need to input into this, into the clustering step, and we did it for, I believe it was 20 subjects, we see that for all of the windows, we can group things very, very well. There is almost a perfect agreement. What we can also see is there are a few And the color basically tells you, we use a metric called the adjusted run index, for which there is this interpretation that as long as it's above 0.9, you're having very good agreement between the groupings that you are expecting and the groupings that comes out of the data. Between 0.8 and 0.9, you're doing good, then moderate and poor. But here the take-home message is that overall we were doing really, really well, yet there are a few subjects that they seem to be not doing that well all the time. Because we have some measures, because as subjects were doing the task, we took responses, we can go back and look to see if maybe those are the subjects that maybe weren't doing the task as well as consistently. And that was the case. When we look for correlations between the classification accuracy and measures like percent correct, response time, and missing responses, we can always see that the three guys that actually make the algorithm perform the worst are the three guys that seem to have been doing the task more inconsistently. So again, one more positive step towards this idea that there might be a relationship there to look for. Here is another study in which they look at this a little bit differently. In this case, if I remember correctly, they have quite long scans in which the subjects were looking at a crosshair, and then only in a few instances a white dot would appear on the screen. And that white dot, only in a few of those instances, would change color, and whenever it was a change in color, the subjects were supposed to press the button. What they were trying to do was to see if the connectivity between the full mode network and the task positive network right before the actual occurrence of one of those task events could help predict how fast they were going to go on their responses. And the answer, and to do that, what they did, first of all, because they really wanted to have a very fine-grained temporal resolution, they just acquired, I think it was only 4 slices with the right angle to cover enough nodes of these two networks, and that allowed us to have them to have a very good TR. And then they computed these very detailed traces of correlation between these two networks. And what they did is they separated their subjects in two groups, the guys that responded really fast to the task and the guys that didn't respond that fast to the task. And what they saw is that they could find a difference in these correlations right before and right after the occurrence of the test in such a way, or the claim was, that looking at the connectivity in the task positive and the test negative in a few seconds before the task can actually help you predict the response time. One more step in which people have looked at this is this potential use as biomarkers or as or potential clinical applications of looking at the variability. So here what we have is the results by the group of Beans-Calhoun, in which they look at these functional states, functional connectivity states. In this particular case, they computed 5 functional connectivity states, and they have healthy controls, and I believe in these studies they have schizophrenic patients. And what they find is that there are some states in which the dwell time in each of, so let me get one step back. So once you have these states and you have a timeline of them, you can start computing metrics. Like you could try to apply some algorithm to the data, and every time it will give you maybe a different number of states. And maybe the number of states, it's an informative bit. Or you can do an algorithm in which you have preset states, and then you can look for those and actually look at the evolution of how that subject navigates through the states. Another way of doing that is you have your states and you can compute dwell times for how long given subject is in each of the states. And that's what they did in this case, and what they found is that dwell time actually was able to differentiate between normals and schizophrenics. So once you start looking at dynamics, so it's very hard when you have fMRI data, which is, hundreds of measures across time, across thousands of voxels, to come with a few numbers that might be informative. Suddenly, when you're doing at the dynamics, you kind of multiply in that space of potential things that you might use as either potential biomarkers or as units that tell you something about the brain. So here is one potential example that seems to help to differentiate at least between normals and schizophrenics. So, conclusions about this second part of the talk. Dynamic changes in functional connectivity, again at the scale of seconds to minutes, meaning within a run, reliably allow to do sleep staging based on fMRI, not on EEG, discriminate between externally imposed mental states, and even potentially predict task performance. I didn't go too much into the details, but it's also good keeping in mind that each of these studies had a completely different set of parameters. They somehow differ in their preprocessing. They somehow differ in the parcellation scheme that they use to compute these connectivity matrices. Then once they have then whatever algorithm that they gave it to either do the classification of the clustering, and what was their metric to validate that in truth there was a relationship between the functional connectivity changes and whatever was the metric of interest. So that being said, it's not only good to be aware of it, but it's also good to think that maybe there are some of these methods that are better at capturing the variability of interest, while some other methods might actually capture the variability due to the noise. And there is a lot of work to be done about what's the best way to look into the dynamics of connectivity in fMRI. Because of that, comparison of consolidation across the results, it's quite challenging. That being said, as I saw, some people have decided to go one step further and actually see if there is potential clinical value. So that takes me to the last part. So any questions about this second part of the talk? Okay, so last part. Okay, so some methodological considerations, and this is just some of them, okay? There are a lot of other things, but just to bring you awareness that things that may intuitively look like something we can very easily interpret, you have to give it maybe a second thought sometimes. And one of the ones that have caused perhaps more of the controversy is this whole idea of a sliding window analysis. It's very straightforward. I think it's the first idea that will come to the mind of many of us. And just because you see this variation and you say, well, I took it here, I computed, took it there, I computed, it kind of feels like, okay, that's something interesting, but we have to think about it a couple of times more. Not only that, but there is, as I said at the beginning of the talk, many questions. What is the window type to use? There's not only square windows. You can use a Hamming window. You can use a window that actually gives more weight. So if you're trying to compute something at this time point, there is some proposals there in which what you do is you give more weight to the connectivity, to the time points that are closer to the point at which you're looking, and then it goes down in giving value of what's later in time, meaning far away in time. So that's another potential thing. What's the optimal window length? I tend to think of this like Google Maps. If I want to find the house of my friend, looking at Google Map at the continent scale might not help me that much. I need to look at the level of the city. And the other way around, if I'm looking for something generic, maybe it makes more sense to look at the continent level. So again, here, what's the optimal window length? And most likely there is not an optimal window length. There are different ones. What's the window step? And I could put many other questions. As I was saying, it seems to be a very easy to interpret method. It seems to capture phenomena with potential biological neuronal relevance. And by that, I mean not just because you look at it, but because of all the studies I've shown, including some of our own. But, two small windows can render correlation estimates that are unreliable. And it's not about only the window length, but what was your original TR, because a window length of 20 seconds is not the same whether you have a TR of 2 seconds or a TR of 0.4 seconds. So those are considerations to take into account. And also, hopefully, I will convince you that the interpretation is a little bit more complex than it seems. There's been several papers on the last 2-3 years kind of pounding on this idea that be careful if you're doing this or not just doing it and thinking all you see is meaningful. One that I would recommend is this one that I think came out in May. And here they talk about several different pitfalls, but one pitfall they address at the beginning is that this idea that to identify and observe value of a statistics as its true underlying value is not a good idea. To just suddenly say that because I see this guy being well below this line, which is the overall connectivity, that doesn't mean that it's dynamic behavior. This is just one measure out of many. And I have to give some confident interval to this measure itself to actually be able to tell that this particular connectivity at this time point was significantly different from the mean one. So if I were to actually, if we were looking, so again, here we have two real-time series. Here we have what would be their overall level of connectivity, or if we were to compute the connectivity using the whole time series. And here we have on the dark black the trace of sliding window correlation connectivity. So the first thing that they say is you need to compute some confidence intervals, and they provide different ideas about how you should compute these and things you have to think about. So if I were to do that, maybe it's okay to say, okay, so at this particular point in time, connectivity that I measure is definitely including the confidence interval outside of this. But let's say that instead of doing that, what I say, okay, in this whole graph here, there are 4 time points here in which it seems that the dynamic connectivity differ from the static connectivity. Well, I will have to put a confidence interval on that to actually know that 4 is something that I wouldn't find by chance, okay? And to go into more details, I highly recommend that paper. So this is one potential pitfall. The other one is to be aware that when we're doing windowing, we're doing some things to the signal. We're setting constraints on what are the frequencies that we can actually explore, okay? So this is a very silly toy example based on this paper, which it's another good one to read if you're gonna try to do this analysis. So here we have 2 sinusoidals, which is a very simplified version of any signal that we'll be considering. They're slightly off in phase. Here what I'm depicting, and hopefully the video will work, is the length of the sliding window that I'm gonna use to compute correlation traces, okay? The evolution of correlation traces. If I were to use the whole set of time points here, because of that shift in phase, the static value of connectivity would be this. If I use this sliding window that you see here, that is much less than the whole duration of a period of the signal, we would see all these fluctuations, which, you know, we would even claim there are moments where it is negatively correlated. What I will show you in a second is as we keep increasing the window length, the moment that we hit a window length that actually includes a whole period of the signals, then, yeah, we still have some fluctuations depending where we are, but at least the values that we compute are more within the range of the actual one. So here, I mean, these 2 signals, their correlation is static. Yet, if we don't use an appropriate window, we might actually infer that there is big variations of correlation. And this, can be shown. So a good idea when you're gonna do any sliding window correlation is if you cannot choose your window, if you set a window, then you have to do at least some high pass filtering. So anything that is too slow, you're removing it from the signal before you actually compute the dynamic traces of correlation. And the same is true if we were to look to 2 real signals. So here there are 2 real signals. This is their dynamic traces of correlation for window length of 180 seconds using the appropriate high order pass filtering, getting rid of anything that doesn't fit in those 180 seconds. If we keep reducing the window length and we don't do any filtering, which is here depicted by the dashed red lines, you can see there is a lot of other fluctuations that are kind of artifactual, okay? And this is not just not math. For example, in our study, we actually found that when we try to do the classification and we do it without using this simple filtering step of Wilde filtering, for the shorter windows, we actually see that things get better, okay? Another thing that might be something that you would think it's easy to interpret, but maybe it's not this whole idea, okay, the longer the window, the less that the observer, the less the amount of variability that we see. Maybe, but it's also good to be aware that when we're doing a sliding window analysis and we're windowing on the time domain, that also sets a constraint for the maximum frequency of the traces of correlation that we calculate. So one thing is to actually do the appropriate filtering in the time series. The other thing is how by doing this, we're setting some minimums or some maximums in what are the variations in correlation that we're gonna observe. And basically we're setting a filter by 1/W. So anything that is faster than that, not on the time series, but on the traces of correlation, we're not gonna be able to see it because it's gonna be quite dampened by this filter that is just happened by the fact of doing the sliding window analysis. So here, also from the same paper, here we have 2 time series. Those are real time series from 2 regions of the brain. And what we can see is that when you compute the sliding window correlation, we can see nothing, when you do the sliding, not the sliding window correlation, when you, compute the spectrum of the time series, the first thing you see here is that they did the appropriate filtering. So anything that was too slow on the time series, they remove it, and they only kept what's above. That's for the time series, but for the actual correlation traces, which is the second point that I was trying to do, what you can see is that both for the sliding window covariance and the sliding window correlation, anything above this 1/W, you almost don't have it. If you were to be computing point-wise correlation, point-wise multiplication between both signals, which is a very noisy way of doing this, but just to prove the point that there are fluctuations well above that frequency cut, but you would not see them just because you're doing the sliding window analysis. So spurious fluctuation in dynamic connectivity can be limited by using the appropriate filtering on the time series prior to computing the correlation, but be aware that when you're setting your window, you're also setting yourself to what's the maximum fluctuations that you will be able to observe, and also to be aware of the influence of not only the window length, but also the TRs. So that regarding the sliding window. That's just one of the decisions. I mean, as I said, another decision is which are the ROIs to use. So it seems there are several studies out there because nowadays, there's many parcellations that you can select to do this type of analysis. But there is, I think this is not the only one, but I like this one, in which they saw that for this type of analysis, you seem to do better if you use functionally based parcellations of the brain versus anatomically based parcellations, okay? So that's one decision. Yet within the functionally based parcellations, there is many of them. In our particular study, because we had this expectation of how things should work, we could actually play with some of the parameters. What we found out is that we went for a functionally defined parcellation, in particular the Craddock Atlas, but what we also find is that the number of ROIs that you use really affects the quality of the results. And in our particular case, what we found is that it's better to use more smaller ROIs than less larger ROIs. And I think that's a very easy interpretation. If you use too big ROIs, you're gonna get one time series representing that whole ROI. If that whole ROI is not functionally homogeneous, which is most likely not to be, the bigger those ROIs are, the less likely that you're capturing information. You're just washing out effects. So that really affects these classifications later. Another important thing, and this is just a very tiny example, is what is then the algorithm that you use to either define these functional connectivity states or groupings. So again, in our particular case, we just play with two different clustering algorithms, and we found that actually k-means outperform hierarchical clustering. So this is just to make the point that, depending on your decisions for preprocessing and analysis, the strength of the relationship between functional connectivity states and cognition or clinical outcome might actually vary. And there is still a lot of work to do to decide what are the optimal ways to do this. There are other metrics to do this type of analysis. Sliding window correlation is not the only one. I mean, that's why we spend some time of understanding whether it's the best one or not, because there are other options. Here again is just one example. This is called dynamic conditional correlation. This is something that has been borrowed from the financial literature. If you want to learn a little bit more, I would recommend you to read that paper. But initially it has two good things. First of all, it does not require an a priori selection of window length. So this whole idea of what's the optimal window length, what's the window step, the model takes care of it. And also, it seems to be quite robust against some of the limitations that I just described. And here are two examples. So here is what should be the actual trace of dynamic evolution of connectivity that they were to be expecting in this simulation. Here we have the actual one that gets calculated with different methods, one of them being this DCC method. Hard to see there, but when you actually look to the error between the actual expected one and the other one, it seems that the DCC seems to be the one that makes, that does best. And some of those are different sliding window with different durations. So it seems that this one seems to be a better option for this type of very slow fluctuations. They also have simulations with another type of potential dynamic behavior in which you have kind of a steady connectivity and then there is, a transient there. So also in this case, it seems that, this DCC metric seems to be quite good at picking it up. So this is a potential thing to consider. And I would recommend that if you're doing this type of analysis, it's always a good idea to compare several methods and make sure that your conclusions hold across them. Another way in which people have decided to look at this concept of Dynamic connectivity is this idea of caps or coactivation patterns. Here the idea is that you basically look at every single time point independently. For every single time point, you can get a map of magnitude, and then you can try to take all those map of magnitude that you have across your time series and try to do some clustering with them. And what they have observed is that then you will get a few of them similar to the functional connectivity states, but those are maps of ball signal, and that those are recurrent and that you can decompose the networks that you normally observe into several of those caps. So again, in this case, if you're interested on that type of analysis, this is the reference to look for. Okay, so just to finalize, I hope at this point we're all aware that functional connectivity exhibit rich spatiotemporal dynamic behavior at the scale of minutes to seconds within a run. Just again, saying the same thing again, they will differ in many aspects from what you would get as your average patterns of correlation. Some of them are recurrent across time. Some of them we can find correlations with behavior, even with some clinical outcomes, or not clinical outcomes, but at least help us differentiate clinical populations. But there is a lot of work to do. And I think three things to take home and think a little bit more about it is that we need to better understand which methods actually capture biologically and neuronally relevant functional connectivity dynamics versus simply noise or spurious correlations that we might be introducing during the analysis. It is unclear to which extent it's actually better to conceptualize dynamic functional connectivity as a multi-stable space state, meaning there are these units that you go back and forth, or it's a continuous. And that will definitely affect how you analyze the data. And also, I think that if we accept that this dynamicity, it also raises the question of whether the concept of a network, what is that? Because it's rather elusive if we know they're breaking in and out continuously during the duration of a scan. So again, and this is hopefully gives you awareness about the topic, awareness about the concerns, but if you were to want to do it, I guess some generic guidelines might also be helpful. So I would say that if you're thinking about doing some study that involves an analysis of dynamic connectivity, there is always this trade-off between temporal and spatial resolution. For this type of analysis, I would give up some spatial resolution to gain temporal resolution, especially if you're thinking about doing some type of analysis that is based on ROIs later. There is no need to have 1,000 voxels in each of the ROIs, okay? Definitely, if you're going to do this type of study, I would seriously consider taking advantage of some of these newest multiband sequences that allow you to acquire several slices per excitation pulse and can reduce UTR by a factor of 2 or 3. In terms of the data preprocessing, I think it's very important to do the appropriate filtering, take into account that. I would definitely consider using at least 2 methods to look at the data. And in terms of the window duration, should you actually decide to look at these things, I mean, there is no magic number, but definitely in the literature, it seems all these studies tend to go around these 30 to 60-second windows to be a window that actually allows you to capture cognitively meaningful variations in connectivity. Regarding parcellation scheme, as I said before, it seems that for this particular type of studies, I would suggest going for some functionally defined ROIs. And within those, I would say, usually more than 100 or 200 ROIs is the minimum you want to do. You don't want to do 30 ROIs that cover the whole brain. Be aware of interpretational challenges. Definitely control for all the things that you would normally have to control in your fMRI studies, motion, physiological noise, everything. But whenever possible, design your experiment in such a way that you can have an external measure that allows you to validate what you're looking at. In our case, we use the imposed task. In the case of the study about predicting, they have the response time. I know sometimes that's not that easy, but give it a second thought of trying to have an external validation metric if possible. And if you're really interested in this topic, I would definitely suggest reading these 2 review papers that have appeared, not that recently anymore, but still I think they contain a lot of information that is valid as of today. So that's all I have. Please, if you have any questions, please ask me. Okay. Well, you know how, I mean, my name and my email, I'm sure it's on the website, so you have any questions, feel free to send me an email. Thank you.